so thanks very much to Svetlana for doing that lovely talk. So I also fall in the same category as her with regards to my relevance to the conference. So I'll also be working in the areas covered by the main lectures. But in particular, so I'll be looking at square function estimates. So the context is similar to what was just presented. I'm interested in solving boundary value problems on domains. So you start with a boundary value problem, and as you saw, the solution then can be represented as some singular type integral. So the singularity is occurring at the boundary of the domain. And so you're interested then in estimates for those kinds of singular integrals. And so one is then led often to study what is the so-called associated square function estimates for singular integrals. And so that's what I want to speak about today. And in particular, so the situation for smooth domains, I guess, was well known in some sense before the 80s. And then in the 80s, it sort of moved into the area of Lipschitz graphs with the seminal paper of Codimensional. They proved boundedness of Cauchy integral on Lipschitz graphs. And after that came these standard techniques, or what are now become standard techniques, tier 1 theorems, tier B theorems, local tier B theorems. They sort of came out of that result, and that's in particular what I was speaking about today, a local tier B theorem. And so after that period, then who've written some marvelous work, were then asking the question, well, where can we go beyond Lipschitz graphs? So what's the least amount of regularity these techniques can be adapted to solve for boundary values? And so that's the notion of an ADR or an L-force to be regular set, and the notion of uniform rectifiability. So let me just mention that it is joint work with Steve Hoffman, Dream and Treya, and Marius and Treya, and it builds on this seminal work of David and Sims. In particular, I'll talk about arbitrary codimension. So let me just set up the here's the overview. So I just want to state a local TFB theorem, which requires me to talk about ADR sets and give you some machinery to understand the statement of that theorem. The main result then is an inductive scheme for square function estimates. Okay, so if you have a square function estimate on a set, then you move to a less regular set by some inductive argument. You can get square function estimates on less and less regular sets. And that's the main idea. And the proof will proceed via the local TFB argument, first of all. And finally, an application will be then uniformly rectifiable sets, okay? Which is the idea stated by the David Sims that it's the least regularity that you can expect to have boundedness for things like simulation. And so two main underlying themes will be, since we're using techniques from harmonic analysis, the scale invariance and quantitative estimates. So uniform rectifiability, for example, you can regard as a scale invariant quantitative version of rectifiability. And let's start with some notation in the setting. So in particular, there's the notion of an L-force to be a regular set. So this is also a quantitative scale invariant version of regularity. In particular, E will be sitting in Rm, and it will be a D-dimensional set. So arbitrary codimension is allowed. E is necessarily strictly less than the ambient dimension. And now the Hausdorff measure of any ball intersected with that set is equivalent to, in a uniform sense, the Hausdorff measure of the usual ball after the dimension of E from. Okay. So that's the notion of L-force to be regularity. You already see the scale invariance and the quantitative nature of this setting. In particular, our singular integral operators will be these guys here, where the theta, the lowercase theta, is satisfying the usual sort of Calderon-Zeeman type conditions. So I left out a little bit of information about where the x, y, and z live, but it's the usual kind of flavor of this. In particular, one point to note is the D here. Okay? So in the Calderon-Zeeman estimates, bound on the kernel is in terms of the dimension of the set E, not the ambient dimension M. but we're interested in particular in arbitrary codimension. Right, so just two technical tools that we need in order to state the local TFP theorem. The first is that in this setting we have the usual dyadic cube structure, or not the usual, a dyadic cube structure. It was constructed by the V 1988 in this context and generalized to more general space of homogeneous type. In particular, it just gives you a dyadic cube at each scale, k being an integer, where the length of the cube will be the usual 2 lines. And in particular, we can then also define a Whitney covering of what's outside of the set E with respect to those dyadic cube compositions. So, for instance, let me just what we can expect here. So, just imagine, so E now is, we're going to draw it rather smooth just to illustrate the point, but of course I'm just assuming that it's helpful to be used rough as anything. So we have, in this case, my set E is one-dimensional, and the ambient dimension is the pages too. Okay? So in particular we have this dyadic cube structure, so these are maybe the dyadic cubes, say at some level, cube, so this guy here will be the cube. So in the complement of E, that's everything above and below this line, we do a Whitney decomposition. So particularly, you can imagine we've got some Whitney box sitting like this at some level, and then as we move it closer, we get smaller and smaller sets. This kind of business. And so then what we call the tent, or the Carlson tent over a cube, is just the union of those Whitney boxes. And so all of this is all lumped together. But this is an arbitrary construction that works for any L force to be reduced. Okay? Also in arbitrary codimension. So instead of just a page we consider three-dimensional space, we could also do that same sort of Whitney wrapping. So the Whitney things would then be three-dimensional boxes, rather than two-dimensional spaces. Alright. So that's just the technicalities. So here's the statement of the theorem that Ariel mentioned a version yesterday, and really the only difference between that version and this version and this one is in arbitrary codimension. I'm not going to mention the proof since it follows exactly the same as the one that she mentioned by Anna Grau and Steve. But in particular, the idea is, so coming from the T of 1 theorem, which says that T of 1 is in BMO if and only if you have a square function estimate. And you show T of 1 is in BMO where you have to establish the Carlson measure estimate. Then the idea with Carlson measure estimates is you really only need to test whether or not you're a Carlson measure on big pieces of each cube. And that's essentially the idea of this local TP. So 1 and 2. So all of these constants are uniform for all cubes. Okay, so that's your scale invariant 1 by E. And then you have this uniform control of your operator in terms of these big cubes. So for each cube Q, you have these functions BQ. And then you derive the square function estimate that we're interested in. So this is the square function estimate that's associated with singular entities. And I will specify I'm just interested in L2 theory. Because the idea is once you have an L2 theory, you can extend to LP to interpolation covering different types. Right? And one can do that in this setting too. But I do want to point out the arbitrary codimension is cropping up in this term. Ordinarily, so n minus d here, that's your codimension. And your ambient dimension d is the dimension of your set E. So I think it's more familiar if we perhaps look at an example. Just go back into the codimension 1 case. So your ambient space is Rn plus 1. The set E is just Rn. So then the complement is going to split in terms of the upper half space and the lower half space. So then your square function estimate, so the distance from any point in the upper half or lower half space to Rn is just, say, if you're at a point yt, where y is in Rn, t is a real number, the distance will just be t. So you recover the usual familiar-looking square function estimate. And since we have a preferred direction, we often usually just consider 0 to infinity and the other ones. Alright? Now when you move into the higher codimension, then you have there's no longer this specified single specified t direction. So you've got just the distance. I like to lump the distance in with the operator. In some sense, this is the visual object which you study. And so over here you see the scale invariance as well, the distance to your bounds. So that's just a slight distinction when you move to the higher codimension. And so here is the main idea that will proceed by this local TP that I presented a minute ago. The idea is we want to establish a square function estimate of this form. So this theorem here says, well, you don't actually need to know that. All you need to prove that is that you have that square function estimate on suitable big pieces of your set E. So that's what this acronym here stands for, big pieces of square function estimates. So again, you have this quantitative uniform idea of square function estimates for each cube on your set E, there exists some other set E cube. So perhaps it's a good idea to draw a picture of that. One cube sitting like this. Here's E. So for each cube there exists some set E cube, which doesn't have to, so maybe it's going to be doing something like this. So this part here, let's say the intersection of E cube with Q. Q is of the same dimension as E, and it's enough to know that you have square function estimates for the operator just on that large portion of that cube, as long as you have uniform control of the square function estimates for all cubes. And then you can divide the square functions. So I will present proof briefly. So all we need to do, since the conclusion, which I just rubbed off, this conclusion here is the same conclusion as the local TOV theorem that we had a few slides ago. So all I need to do is verify the three conditions of the local TOV. And those are going to follow from geometry and the big pieces assumption. Okay, so the BQs that we define are simply the indicator functions of the cubes intersected with those big piece sets EQ. 1 and 2 are rather trivial. Well, number 1 is completely immediate. An integral of BQ squared is just an integral of 1, which of course is bounded by the measure of Q. So that's 3. Number 2, the big pieces square function property guarantees this thing over here. I think that was part of having big pieces. That each cube, Q intersected with each EQ contains a uniform big piece of the cube. So we get number 2. 3, the hard work comes with number 3, but it's also not that challenging. So remember, here we're trying to prove that we have control of this integral over this 10th region in terms of the measure of the cube. So we break it up into 3 pieces. Okay? And those 3 pieces depend upon the relationship between the distance to EQ and the distance to the step E. So notice in this estimates here we've got distance from S to E, but in order to verify, in order to use the big pieces properties, we need distance to EQ. So that's why we're comparing with E and EQ in those estimates. Okay? So delta is a constant that you need to choose in order to make everything work. So A and C they just require properties of the kernel and the geometry, right? And that's the more technical nature, and that's where you have to fix the constant delta. So rather than go through those, I will just illustrate the integral on the B part, and that's just so first of all here I take away EQ, since it's a lower dimensional set, and now I just can replace the distance with the distance with EQ, because on B was the region in which the distances were comparable to 1. And then of course I can use the region, and then this property here is the big pieces square function estimate. Okay? That is, we knew these square function estimates, we knew this fell on big piece, and then the last part of this. And so the proof is rather straightforward, barring those technicalities. Okay, so that's the end of it. So I guess I have no idea at the time. I have one application open at 1 minute. So in the very last minute, let me mention the application, and really the main reason for doing all of this is to understand uniform rectifiers. So David and Sens in 93 proved square function estimates for this particular kind of operator. In fact, they just look at the Cauchy integral. agree with the proportional property. So that's what they proved for a uniformly rectifiable set. And so we now have proof of that sort of incorporates local TOV technology rather than the original proof, which was suited by Corona type arguments, something you might be familiar with. The idea is we can just go from having any big pieces of estimates to just getting estimates now from our main theorem. And a recent result of the Zaman-Schul is that uniform rectifiability is equivalent to big pieces squared of Lipschitz graphs. And square function estimates are well known for Lipschitz graphs, so the implications come through. Thank you very much.
Thank you. Questions?
Do you have a singular interval?
No, we don't have a singular interval model. Even for TOV, no, well, we haven't done it. I mean, David and Sons have it.
Yes,
Many
original theories of
Yeah.
singular integrals and I mean, does the sandwich would be easier to apply in any case supported by, I mean, as in checking, singular integrals of particular functions, one against one measurement, easier to do than checking square functions. No.
Oh, and let me actually make the point that rather important point. So the main result here, not this one, the one where we just had big pieces in closed square functions, that's for arbitrary codimension. So that big sort of measure theorem works in arbitrary codimension. This result here relies essentially on having square function estimates for Lipschitz graphs, which is only known in codimension 1. So we only get this for uniformly